Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. And we are in the middle of, or you should be in the middle of, learning about power series, Taylor series, and Maclaurin series expansions for different functions. And in the process of learning this, you usually are asked at some point to evaluate an integral. And generally speaking, it seems out of place in the material, especially if they don't tell you to use power series to do so. However, this integral, you could try to evaluate it other ways, but it actually is somewhat easy to use power series here. So there's a good use of power series. Let me simplify this. There's two ways to go about this. Actually, maybe what I should do is down here, I'll put equals, and this is the first way that you can do this. You can break this into two integrals, the cosine of x over x and dx, and then minus the integral of 1 over x dx. At least one of those you happen to know the value of. You know that the second integral, let me go ahead and write this out, is equal to the natural log absolute value of x. Now, I noticed I didn't write the constant of integration there, and the reason why I did not write the constant of integration is because I have it still within the other integral. So the integral, the first integral, when I evaluate that, will finally throw out the constant of integration. Now you could try to integrate that first expression by parts. However, I'm going to go ahead and rewrite the cosine here as a power series. And we know the cosine is an alternating series, x to the 2n over 2n factorial. And that is being divided by x. And then dx minus the natural log absolute value of x. And of course, you can simplify that. That division by x will divide into each one of those x's that are in the numerator. So that's going to be a summation n equals 0 to infinity of a negative 1 to the nth x to the 2n minus 1. That's me dividing each of those terms by x over 2n factorial. And then, of course, we have the dx on the outside. And minus a natural log absolute value of x. Now, something interesting happens here, and I actually want to showcase this because it is important. So if you were to integrate this, you want to make sure that all the powers are not, you don't have a negative 1, because the negative 1 power is an issue. And so let me just showcase this expansion a little bit. If you run this series with n equals 0, you get a negative 1 to the 0th, which is positive, and you get an x to the negative 1 over 1 factorial. And then plus the summation n equals 1 to infinity, because we just ran it only once. And the reason why is because that x to the negative 1, when you integrate that, that is a major issue. That does not turn into a polynomial, as we've just seen with the natural logarithm. So you have to be kind of careful with this specific one. X to the 2n minus 1 all over 2n factorial. And this is dx on all of this. And then we have a minus natural log absolute value of x. If you integrate that first piece, that's just a 1 over x, and that integrates to be a natural log absolute value of x. So you could see the natural log absolute values of x's will cancel. Okay. And I still have an integral from 1 to infinity of a negative 1 to the nth x to 2n minus 1 over 2n factorial. Now, because a lot of people are not going to see that negative exponent of negative 1 within the power series before they integrate, this can be a very dangerous problem. However, it's doable a different way. We'll show in a second. Let's see. I'm going to kill off those natural logs at least. And as we've learned previously, when you integrate a power series, you can integrate term by term within the series. So this would actually be I'm going to write a summation here. Notice I left a little space out front. There's a specific reason. N equals to infinity. Notice I didn't write the index yet. That's also on purpose. And let's see, -1 to the nth is a constant. And when we integrate this piece right here, you're going to raise the power by 1. So it's x to 2n now. And you're going to divide by that new power. So you have 2n times 2n factorial. Okay. But you know when you run an integral, you get a constant of integration. So I'm going to put the plus c out front, because if I put it on the right hand side, it looks like that c is within the summation. So I'm going to put it to the left hand side there. Another thing I want to mention is when you integrate a function, for example, just as an aside, let me scoot over here. If you were integrating x squared plus x, let's just make it easy, right? You don't really gain any terms other than the constant of integration when you integrate. In other words, this will become x cubed over 3 plus x squared over 2. You didn't gain anything else except for this additional constant. So after you run an integral, you don't gain anything other than constant. And if you look back over here, we started at 1, we ran the integral, and we should have no more or no less as far as terms go, except for this constant c. So we should still start at 1. And if you're following my video series, or if you're in my class, you already know that I talk about this. With differentiation, you have the possibility of losing terms. So with differentiation versus integration, you need to be very cognizant or aware of the terms of your series to know that if the first term is going to be a constant, then when you differentiate it, it will disappear. You've lost a term on your series. But anyway, integration, you still start at whatever your index was before. And that's actually the answer for this problem. But I'm going to do it a different way just to showcase kind of how you can be a little bit more careful with this integral. So the integral is the cosine of x minus 1 over x. So if I just, here's a second way, if I just write the integral of the cosine of x, which is n equals 0 to infinity of a -1 to the nth x to 2n over 2n factorial, minus 1 all over x and then dx, you'll notice that the very first term of this expansion here is 1, and then it goes minus x squared over 2 factorial and plus x to the 4th over 4 factorial, so and so on and so forth, dot, dot, dot. So this positive one right here and this negative one right there will cancel. And so it's sort of like me saying, you know what, I'm going to integrate the series, but I'm not going to start at 0. I'm going to start at 1. I'm going to ignore the 0th term, and that will, because that's going to cancel the -1 right here. So these two terms are going to cancel out, and it's just as if I had ran my series starting at 1 from -1 of -1 to the nth x to 2n over 2n factorial divided by x dx. And then you can see at this point, this integral is going to be the same as the integral we saw a moment ago, but without the consideration. Let me clean this up a little bit. -1 to the nth x to 2n minus 1 over 2n factorial dx. And this is going to be the same integral that we ran just a second ago. So let me scroll up to show you. It is actually, let me highlight it, this integral right here. It's the exact same integral. So even though we could break that integral, that integrand apart right here, cosine of x over x minus 1 over x, we could do that, and we'd end up just kind of, stepping through the process. When you're dealing with power series, sometimes it's nicer to keep things together and clean them up, keep the integrand together, and then integrate, because this integral will end up being the same as we've just computed right here. Anyhow, so there you go. Two different ways to do this problem, and a very nice view of how to integrate using power series. I hope this video helped you, and if you do like it, please click the like button, and go ahead and watch the next video in the series if you have the time.